All right, I got a new term for you now. And because we've been learning some different terms, and some of those terms are easy to remember and some of them are harder. I definitely expect you to know the term adiabatic. You got to know that one, right? No heat transfer? You got to know that one, right? And I definitely expect you to know isothermal, right? Constant temperature. You got to know that one. Those are two you can't forget, okay? Now, there's a few other ones that you might not remember so well, like isochoric means constant volume, okay? Another one that you might forget about is the polytropic processes. That's where PV to the N is a constant, right, for a polytropic. Those I know might be a little more fuzzy to you. But there's another one that's in the class of adiabatic and isothermal that you got to know. And that is isentropic, okay? Another useful application of entropy is that it can be used to connect two states. Okay, it can be used as the connector. So you have information about one state, but you don't know everything about the other state, but you know it's an isentropic process. That gives you some more information. Because an isentropic process is one that has constant entropy. So you're basically going to write S1 equals S2. Okay, so isentropic is a very important relationship. Okay. And we're going to use that quite a bit. We're going to make that as an assumption quite a few times, and it will be an important connector as we go on, okay? Isentropic. So, remember there's two ways in which we can change entropy. Entropy can poof come from nothing, right? How does it poof come from nothing? Friction. A lot of times that's friction or unrestrained expansion of gases, things like that. Or entropy flows with heat, right? Okay. So here's the deal. Are all internally reversible adiabatic processes isentropic? Meaning, if I don't have any internal entropy generation and I don't have any heat transfer, is that isentropic? Yeah. Yeah, that's it. You can have entropy because of internal generation, and you can have entropy because of heat transfer. So if you don't have either one, then that must be an isentropic process. Yes? No, isothermal doesn't mean it's adiabatic. It doesn't mean it's reversible. I mean, there's lots of things. There's lots of cases where isothermal may not be isentropic. Okay? But there are some cases where isothermal could be. We'll get to that as we go. But, you can't generally assume that at all. How about the reverse, though? Are all isentropic processes both internally reversible and adiabatic? How about the reverse? Because, honestly, internally reversible and adiabatic, that's pretty tough. That's tough. I mean, there's not really anything out there that's both internally reversible and adiabatic. Not real processes, okay? So that's a tough guideline there, okay? But the answer to this one is no, okay? You can come up with isentropic processes that are not internally reversible and not adiabatic. And it's actually a really simple example. Remember when I talk about internally reversible, meaning like no friction? Like nothing on the inside is causing any irreversibilities. And so, lose some heat, but gain some entropy on the inside, and they balance each other out, okay? So isentropic, assuming it's isentropic, does not mean it's some pie-in-the-sky concept that never could happen, okay? Isentropic processes can really happen with real processes, okay? Because you can lose the heat, but also have some internal entropy generation, okay? So this is okay. This doesn't mean that you... it's not realistic. So some isentropic processes may be irreversible and non-adiabatic, okay? So that's good. That means you can actually use this practically. Okay, so let's do this one real quick here. We don't have a lot of time, but I think we can get this done. Very simple. Steam is expanded in an isentropic turbine. In this case, we're going to assume it's also adiabatic. It turns out we kind of have to do that to make this simpler for us. Okay? isentropic adiabatic turbine with a single input and a single output. At the input, you got steam at 2 megapascals and 360 degrees Celsius. And at the output, you got a pressure of 100 kilopascals. It asks for the work produced in kilojoules per kilogram. So you're probably thinking first law of thermodynamics, and if you are, you're thinking right. Q minus W is equal to H2 minus H1, right? This is per mass, so I'm not writing M. This is per mass. Everything's per mass here, right? Q minus W is equal to H2 minus H1, but I said it's adiabatic, so there's no Q. So this becomes a very simple equation, right? This basically just says minus the work produced is equal to H2 minus H1. So if I can just get my H's, if I can just get my enthalpies, I can easily calculate the work produced in kilojoules per kilogram. All I have to do is get my enthalpies. And the good news is the enthalpy, by the way, sorry. Let me change this. I don't want to interpolate today. We're going to change this. I forgot. We're going to change this to 350. Yeah, I don't feel like interpolation today. So we're going to change this to 350 degrees Celsius. Sorry, I'm lazy. I don't have time. We only got 2 minutes left. We're not going to interpolate. Okay, so I can easily get the H1, right? I can get the enthalpy of what's going in because I know two things. I know its pressure and I know its temperature. And I can go to my charts here real quick here. I go back and this is metric. It's metric here and let's see. 2 megapascals and 350. If I'm 2 megapascals, 350 degrees Celsius, my H is right there, I believe. 3137.7. Does that look right? Looks good to me. 3137.7. Kilojoules per kilogram. All right, I'm almost done. All I got to do is get H2. So how the heck am I going to get H2 when all I know is it's 100 kilopascals? Yeah, that's it. That's our connecting property. The connection is the fact that S1 equals S2, right? So let me get my S1, right? What's my entropy at state 1? Well, I can just read it off the same table, right? My entropy at state 1 is right there, 6.9583. So I'm going to go 6.9583. Okay, and the units are kilojoules per kilogram K. All right, and that means that when I look up H2, I'm going to use that pressure, 100 kilopascals, and I'm going to look for where the entropy is 6.9583. Okay? So what's that going to be? Well, it turns out it's going to be on the saturated. So I'm going to go saturated liquid pressure table. Why? Because I'm given a pressure, right? My pressure is right here, 100 kPa. So if I scroll over to the right side here, ooh, I lost it. Let's see if I can stay sorted. Yeah, there we go. These are my entropies, the last three columns. The first number there is saturated liquid. The last number there is saturated vapor. So is my number between those two numbers? Yes. Right? Is 6.9583. 6.9583 is right between those two high and lows, right? So this is good. I found the right thing. So practically speaking, how am I going to get the H? What am I going to have to get? The X, the quality, right? The quality. So how am I going to get that? Here's what I do. Let me go fast. I'm going to say this. I'm going to say the S that I have is equal to the S of the liquid, okay, plus the quality times the S, what we call the SFG, right? Right? So this is going to be 6.9583. Then I'm going to look for the low value of S there, which is the 1.3028. plus x times that middle value, right? The middle value is the 6.0562. Okay? And to save time, let me see if I can very fast do the calculation here, because I can't remember exactly what that number was. It's pretty high. 6.9583 minus 1.3028 equals that. Divide by 6.0562. 0.93. So you get a quality X of 0.93. Then how do you get H? How do you get your enthalpy? You use that quality, right? You would say that the actual H is equal to my low H, which is, these are my three H's for that value. It's going to be 417.51 plus my quality, 0.93, times that middle value of H, which is the 2257.5. Okay? And if you work that out, times 2257.5 equals that, plus 417.5, you get 2526 roughly kilojoules per kilogram. So that's H2, 2526 roughly kilojoules per kilogram. And then if you 3.37.7, you work it out here, it turns out that H2 minus W equals H2 minus H1, which is equal to minus 612, basically, kilojoules per kilogram. Remember, both of them are negative. So negative of the work equals negative 612. So that tells you that your work ultimately produced is 612 kilojoules per kilogram. Okay. That's all I wanted to say there. So the whole point there is to use now entropy to connect the two states.